In this session, we are going to discuss about equilibrium electrostatics. Now, here, consider the electrostatics of an NP heterojunction as shown in figure. That is, if a heterojunction is formed between an N-type semiconductor and a P-type semiconductor. These are the various labelings that they have given. Delta EV stands for valence band edge, like that. All these terms we have already mentioned in our classes that we have dealt before. So now I am not explaining each of these terms. You can refer back, so you will get what each of these terms stands for. XN, XP, EGP. EGP is a band gap of P-type semiconductor, like that. So all these terms we have already discussed. So please know what each of these labelings stands for. Okay, so this is an NP heterojunction, the energy band diagram of an NP heterojunction. Now we are going to discuss about the electrostatics of this NP heterojunction. Here, though we are considering a heterojunction, first we will discuss about how the potential difference exists in a homojunction. In homojunctions, potential difference exists across the depletion region in both N and P region. This potential difference actually corresponds to the potential barrier on either side of the junction that we already discussed in the case of a normal PN junction diode. Okay, so all these concepts are not new. Then this built-in potential for this ideal case is defined and is shown in figure that is shown here. And then now to be the potential difference across a vacuum level. That is, in a homojunction, the potential difference that is existing across N and P region corresponds to the potential barrier, or potential barrier across the junction. Whereas in the case of a heterojunction, this potential barrier corresponds to potential difference across vacuum level. Vacuum level and all we have already discussed. Now, in general, potential barrier is the sum of potential difference across each of the depletion regions. That is, each of the depletion region means depletion region that extends towards N region and the depletion region that extends towards P region of the semiconductor concerned. Now, in the case of a heterojunction, the potential barrier is not equal to the difference between conduction bands across the junction, or the difference between valence band across the junction. So we know in homojunctions we define potential barrier as the potential barrier is equivalent to the potential difference that exists across the depletion region in both N and region, or potential barrier is equal to the difference between a valence band edge and conduction band edge. That is in the case of homojunction, but in the case of heterojunction there is a slight difference. That is, here the potential barrier denoted as VBI is taken as difference between work functions, that is phi SP minus phi SN, that is work function of P-type semiconductor minus work function of N-type semiconductor. That is how potential barrier in a heterojunction is represented. Potential barrier in a homojunction is the difference between valence band and conduction band that extends across the junction, whereas in the case of a heterojunction, potential barrier is taken as difference between the work function. That is equation 1. See, here they have represented the vacuum level in this figure. So from this figure, our equation 1, that is the equation that includes the work function, can be expressed as this, that is EBI, that is charge of electron into the potential barrier VBI is equal to this expression. If you want, you can just skip this equation and write this final equation. Okay, that is charge of electron in bracket electron affinity of p region minus electron affinity of n region plus the difference between the band gaps plus the difference between the Fermi level, okay, of n region first, and then we are taking the p region. So that EVBI, that is charge of electron into potential barrier, is equal to charge of electron into difference between electron affinities plus difference between their energy band gaps plus electron Fermi level of n region minus Fermi level of p region. This is again expressed as equation 2. Finally, we can write equation 2 as this one. So when you are writing, there is no need of writing all those equations because that will be difficult to study. So you can write equation 1. Then after drawing this figure, we can write from the above figure, equation 1 can be represented as this equation, and finally you can write that equation can again be modified into this one. Okay, that is enough. Then mention what each term stands for. Here P, PO and PNO means whole concentration in P and N region. Then NSN and NEP stands for effective density of state functions in N and P region. So when you are writing any equation, you have to mention the terms that you specify in that equation. Okay, so this you have to mention. Finally, we obtain the expression for built-in potential barrier or potential barrier as this. This is the expression for potential barrier in terms of conduction band shift. So this equation you have to write. Potential barrier in terms of conduction band shift can be expressed as this. So you can, once you write this equation, if you study this equation by making slight modification, you can write this equation. So there will not be much problem while learning. Then now we are going to determine the electric field and potential in the junction. For that we use Poisson's equation, which we have already used while discussing homojunction. So let us see the case of homojunction doping first. For homojunction doping in N region, we have the electric field potential as En is equal to this expression, and in the P region the electric field potential is in this expression. So in the case, so you have to write, in the case of a homojunction doping, the electric field and potential in the case is that is in the case of homogeneous doping, that is homogeneous doping means uniform doping. For homogeneous doping, the expression for electric field and potential is given by this in the case of N region and given by this equation in the case of P region. Here what is this epsilon, P, epsilon, and all these are permittivities of N and P region materials. The other terms we have already discussed in the earlier classes, that's why I am not mentioning those terms here. Okay, so when you refer back the earlier classes, you will get what each of those Xn, Xp and all stands for. Now electric field potential in N region En is equal to 0 when X is equal to minus Xn, and electric field in the P region Ep will be 0 when X is equal to Xp. Then the electric flux density is continuous across the junction. So we can equate these two equations, that is epsilon and En is equal to epsilon P Ep, and that will give you N dn Xn as NAP Xp, that is donor concentration, acceptor concentration. Okay, equation 3, it states that, then what is the meaning of this equation? States that the net negative charge in P region is equal to net positive charge in N region. Now the electric potential, we can find it by integrating the above obtained electric field through space charge region. So potential difference across each region can be determined. Now we find that this built-in potential in N region as this, and the built-in potential in P region as this. Here they are not giving you the derivations, they are just giving you the expressions. So it is enough that you also study the expressions given, no need of writing the derivations. Just write the sentence and write the expression. That is, the built-in potential in N region is this one, and the built-in potential in P region is this one. So using this, equation 3 can again be rewritten as xn by xp is equal to nap by ndn. Now the ratio of built-in potential barrier is again expressed as, so after writing this, you just write the ratio of built-in potential barrier. Earlier we have discussed about built-in potential, and here the potential barrier, that is VBIN, that is built-in potential in N region by built-in potential in P region, is equal to this one. No need of writing this. Okay, VBIN by VBIP is equal to this one. Okay, this expression or that ratio shows that larger potential difference is across lower doped region. That is, lighter the doping, greater will be the potential difference. Hence, the total built-in potential barrier will be equal to VBI, that is total built-in barrier is equal to built-in potential barrier across N region plus built-in potential barrier across P region. So you just add those two terms that we have already discussed. See, here we have discussed these two terms, right? So you just add these two terms, then you will get the total built-in potential barrier as this, equation 4. Now on solving for xp from equation 3 and substituting in the equation 4, you will get the value of xn as this and the value of xp as this. So that also, if you can write, you just write, otherwise you just skip. If it is once you learn this, it is easy to write this, but if you can study, you can just mention, otherwise you can leave it. Now the expression, so we have found out the expression for total built-in potential barrier. Okay, now the expression for the total depletion region width, that will be equal to xn plus xp. Okay, so you will have to study these two terms, then only you will be able to write this expression. If you are skipping these two expressions, then you will have to skip this also. Okay, so once you study this xn and xp, definitely you will have to write the total depletion width also, because that is the sum of xn plus xp, which is this one. Okay, now let us see what happens when a reverse bias voltage is applied across the junction. That is, in this electrostatics, it is actually not a continuous one. That is, in the electrostatics, they are discussing about various concepts. That is the expression for built-in potential barrier, expression for total depletion region width, what happens when reverse voltage is applied, how about the vacuum level, etc. So all these concepts, they are put together. So it's not they are not discussing about a single concept. They are comprising many concepts in under one heading, electrostatics. Okay, so don't think that this is a continuous one. Now here they are discussing about what happens when a reverse bias voltage is applied across heterojunction. So here, if that is the case, we have to replace this built-in potential barrier VBI, we have to replace it with VBI plus the reverse voltage that is applied, that is VR. Now similarly, if we are applying a forward voltage, then we have to replace this built-in potential barrier VBI with VBI minus the forward voltage applied, VA. Okay, what is VR? It is the magnitude of reverse bias voltage, and VA is the magnitude of forward bias voltage. Now Whenever there is a change in the width of the depletion region, definitely there will be a change in junction voltage, and that particular phenomenon is termed as junction capacitance. Now, what will be the expression for junction capacitance for this NP junction, that is Cj dash? It is given by that expression. Its unit is Fermi per centimeter square, Farad per centimeter square. Now here if we plot a graph between 1 by junction capacitance square versus reverse bias voltage VR, you will get a straight line. Now if you extrapolate this plot, we will be able to find the built-in potential barrier VBI. Okay, so this discuss about the concept of junction capacitance. See, first of all, they have discussed about the total potential barrier, total depletion region width. Now they have discussed about junction capacitance and how it will look like, or from the plot of junction capacitance, how will you get the potential barrier. Okay, so that is over by this. Now another concept. Now delta EC and delta EV, what are they? Conduction band edge and valence band edge. Okay, their theoretical value may differ from their ideal value as per this electron affinity rule. Why this difference exists? One explanation for this is that most heterojunctions have interface states. Now, if we assume that the potential is continuous throughout the junction, then the electric flux density, that is capital letter D, will be discontinuous at the heterojunction because of the existence of these interface states. Now these interface states will change the energy band diagram. So that is how that difference comes. That is, once the energy band diagram changes, definitely the values of conduction band edge and valence band edge changes. So that is one possible explanation for why there is a difference between the experimental values and the ideal values of valence band edge and conduction band edge, that is the presence of interface states. Now another possible explanation for this is that as the two materials, that is we are discussing about heterojunction, so as the two materials are brought together to form heterojunction, the electron of orbitals of each electron of each material will interact with each other, that is electron orbital interaction will take place, resulting in a transition region of a few angstrom at the interface. Now the energy band gap then it will be continuous through this transition region and not a characteristics of either material. Okay, so we will get the relation as the change in conduction band edge plus the change in valence band edge will be equal to the energy band gap difference. Okay, so these are the two possible reasons for the difference between the ideal values and experimental values of valence band edge and conduction band edge. Now this particular figure shows the energy band diagram of a NP heterojunction. In the earlier case we have discussed about this one. Now we are going to discuss about this type of heterojunction, the energy band diagram. Okay, here also conduction band edge and valence band edge, which is quite evident from the figure that they are discontinuous. So this difference will influence the IV characteristics also. Now the other two types of heterojunctions are this one. Okay, so we have discussed about how many heterojunctions? 4. That is, we have discussed about this heterojunction, we have discussed about this type of heterojunction, we have discussed, now we are going to discuss about these two type of heterojunctions: capital N small p, capital P small n, capital N small n, capital P small p. Okay, now to achieve thermal equilibrium, we know electrons from valence band, electrons from wide band gap material has to flow into narrow band gap material. Then a positive depletion region will exist in the wide band gap material, and a collection of electrons will now exist at the interface in the narrow band gap material. Since the number of allowed energy levels are high in a conduction band, we expect that the width of the depletion region and also the potential barrier will be small in the case of a narrow band gap material. Now the energy band diagram of this PP heterojunction is shown in this figure. This is the energy band diagram of an NP heterojunction. This is the energy band diagram of a this type of heterojunction. Okay. So in this case, to achieve thermal equilibrium, holes from wide band gap material, because we are all these are p regions, so majority charge carriers are holes. So holes from wide band gap material will flow into narrow band gap material, thereby creating a collection of holes in the narrow band gap material at the interface. These type of isotope heterojunctions, that is of same form, these are all isotope heterojunctions. Okay. Are not possible in homojunction. That is possible only in heterojunctions. That is isotope heterojunctions. So that is all about electrostatics of heterojunction. So I think this you will have to make a note of yourself. That is, make use of this as reference, and then this is what described in your reference text. Okay. So you can make a note of yourself. If you want, you can skip some of the parts that is difficult for you to learn, and take only those that you can write, because I already said this is just a collection of various concepts, not a continuous one. Okay. So whatever you write, there must be a continuity. Okay, if you want, you can draw this diagram, then only you will be able to explain this slide. So as I already said, after writing this equation 1, you can draw this diagram and write this expression, and no need of writing this directly, you can write this equation, and all this you can write. So a few terms you will have to study, then all these things you can write, then expressions for built-in potential in N and P region, then this one, then the ratio, this one is equal to this, then so that is the expression for built-in potential barrier, total built-in potential barrier expression. That is the first concept that you are discussing in this essay. Then you have to write these two terms, then only you can write this one, the total depletion region width, second concept, this one. Then what happens when reverse voltage is applied, and what happens when forward voltage is applied, and the expression for junction capacitance, the third concept. Then this is a fourth concept. What is the reason for the difference between the experimental values and theoretical values of valence band edge and conduction band edge. Then these two slides, if you want, you can skip, no need of mentioning. If it is easy to learn, then you can write. Okay. So just make a note of yourself, that is, take only those concepts that you understand, then it will be easy for you to write it as an essay. Okay. Thank you.